This is a calculus optimization problem. So it says a 216 square meter rectangular pea patch is to be enclosed by a fence and divided into two equal parts by another fence parallel to one of the sides. Of course, if it's a rectangle and it's parallel to one side, it's going to be parallel to two sides. What dimensions for the outer rectangle will require the smallest total length of fence? How much fence will be needed? So let's go back to our, how do we solve an application problem? And the first two items, they go together. What is the question? And what will be the form of the answer, including units? So looking at this, I see a couple of questions. I need dimensions for the outer rectangle that require the smallest total length of fence. So I need dimensions. And then I want the smallest. And that is going to be in meters. That's the units. And then it says, how much fence will be needed? So total fence. And that will also be in meters. Draw a picture. Item number 3. Okay. And I think that's pretty important, especially for a problem like this. So let's draw a picture. I have a rectangular pea patch, and it is 216 square meters. And it is divided into two equal parts by another fence. Let's make that a little bit different color here. Parallel to one of the sides, it's parallel to two of the sides. I think that's really what my picture is going to look like. So I'm going to go back here and I say, okay, set up the equations and solve. Well, what equations do I need? Well, let's add a couple more things to this. Let's call this the height, and let's not call it the height. Let's call this, it's a rectangle and it's flat, so it doesn't have any height. Let's call this the width, and let's call this the length. So what information do I know here? I know that width times length is going to be 216. And I also know that total fence, let's call it TF, is going to be equal to, well, it's the perimeter of the whole thing, which would be 2L plus 2W plus one additional W, my middle divider right there. So total fence is going to be equal to 2L plus 3W. So if I go back to my question, I'm trying to find the dimensions that will make the outer rectangle require the smallest total length of fence. So I need an equation for the total fence that is going to allow me to do an optimization, a minimum or a maximum type of an analysis here using my calculus. But I have a problem in that I have the total fence here is a function of two variables, length and width, and I only know how to do calculus with if I have one variable, a function of one variable. But I can see from this equation that my length is equal to 216 divided by my width. I just divide both sides here by W, and I get length is equal to 216 over W. So now I have an equation here. The total amount of fence as a function of W is going to be equal to 2 times 216 over W, substituting this for the L right here plus 3W. So again, I'm using calculus. So what I need to do is I need to find the derivative. I need to find T prime of W, find out where that equals 0, or doesn't it exist, and then see if that's a minimum or maximum, because that's what I'm looking for. I'm looking for a minimum here. So I'm going to actually just change my TW into something that's a little bit easier to differentiate. I'm going to change this into 432 W to the negative 1 plus 3W. And now I can take the derivative of this fairly easily. If I pick up my pen. So T prime of W would be equal to negative 432 W to the negative 2 plus, well, it looks like it's just plus 3. So that, let's just make it a little bit nicer here. That is equal to 3 minus 432 over W squared. Let's get ourselves a common denominator by multiplying the 3 by W squared over W squared. And I wind up with 3W squared minus 432 divided by W squared. That is the equation of my derivative. Now I need to find out where it is equal to 0 or where it does not exist. So I'm looking for, remember, I'm looking for critical points. F of x, F prime of x equals 0, or F prime of x does not exist. Well, I can see that the place that it doesn't exist is where W equals 0. But I'm not really too concerned about that because I'm dealing with a rectangle. And I clearly have some form of W. I'm not worried about it being 0. So that's really not going to bother me. What I really want to find out is where does the derivative equal 0? And I know that if the numerator equals 0, the whole thing's going to be equal to 0. So for example, 0 divided by 7 equals 0. 0 divided by 123 equals 0. 0 divided by pi equals 0. Anything into 0 is equal to 0. So I need to find out, come on, go away, what makes that equal to 0. So I'm going to set 3W squared minus 432 equal to 0. And I'm going to factor out a 3. I'll divide both sides by 3, and I get W squared minus 144 equals 0, which is really nice because it's the difference of two perfect squares. So I have W minus 12 times W plus 12 equals 0. So I have an answer of 12, and I have an answer of negative 12. But since I'm dealing with a real-world problem with actual distances, I cannot have a negative distance. So I can see that W is equal to 12. Let's test to make sure that that is actually a minimum. That's the only place where my derivative is equal to 0. So here's 0, 5, 10, 15. So here's 12. Okay? And so let's test into our derivative right here. Let's test 0, which is in this interval over here. So I would have 0 for W So that would be a negative 432. So that's a negative slope. And if I have 12, well, I can tell that's going to be 144 times 3 is 432. So anything greater than 12 is going to make this greater than 432. So this is going to be positive. So it's telling me that my graph has a negative slope and then a positive slope. So indeed, I have a minimum right there at 12. So now I can go back to my other formulas here. Whoops, why does this keep moving? Okay. So I know that W times L is equal to 216. So if W equals 12, 12 times L equals 216. That means L must equal, come on, calculator here, 216 divided by 12. Oh, isn't that pleasant? It's a nice round number. L is equal to 18. So my dimensions of the outer rectangle are W is 12, L is 18, and the total amount of fence that I need is 2L plus 3W. So I have 2 times 18 plus 3 times 12. That should give me 36 plus, well, what do you know, 36 plus 36, 72 meters. Actually, this is a meter. Make sure we use our units. And that's the optimization. That's the answer to this problem. I think it's not a bad idea always to check it on a graph, make sure that we're thinking right, although I'm pretty confident in this answer. But I'm going to take the equation of my total fence. So that is this equation right here. Remember, I'm trying to minimize that. That's what I want to see. I want to take that equation. And so I have my 3x, or here it's 3w, plus 432 divided by w. And I'm going to graph it. So I'm going to go zoom 6. And nothing shows up. Am I disturbed? No. It's because I know that I'm dealing with some numbers that might be bigger than just my 10 by 10 here. In fact, what do I know? I go to my window here. First of all, the lowest possible x that I can have is going to be 0. And I've calculated my x as 12. My y is 18. I'm just going to be generous here and say, let's make my x maximum 20. If I didn't know better, I would probably pick 20 anyways, because 216 square meters, if one side was 20, the other side's going to be pretty narrow. It's a good number. It kind of makes sense to me. I'll leave my x scale at 1. Now my y minimum, I know the lowest it could possibly be would be 0. I don't need to go negative numbers because I can't have any y value for any 0 value for total fence. But what's my maximum going to be? Well, again, if I was just kind of thinking, if one side could be 20, let's say both sides could be 20, that would give me 400. My y maximum is certainly not going to be greater than 216. I'll put in 250 just to see what it looks like. And my scale here, since it's 250, I'm going to make it 10. A little bit bigger so I don't have all these tick marks. And then I'm going to push graph. And now I'm getting a graph that actually looks like it does have a minimum. You can't see it that terribly clearly because, you know, the pixels on the TI are not that strong. It's not as good as the Desmos. But, you know, right along here is a big long stretch, but I can definitely see that it starts going up. So somewhere in here is going to be my minimum. So I'll go, I don't want to drag the screen. I'm going to go second, calc, and I'm looking for a minimum. My left bound, well, I thought it was 12, so it's saying, well, right now I have it at 10, so 10 is okay. I'll just put in 10. And my right bound, I don't know, let's make it 20. So there's my boundaries. I don't want to make a guess, and I press enter, and I find out that indeed my minimum is 12. I had the right answer.